Good afternoon and welcome to our latest PSDI webinar. And I'm Dr. Mansur Nelikal, Community Coordinator for the Physical Sciences Data Infrastructure, and I'll be chairing today's session. Let me introduce our speaker. It's my pleasure to welcome Dr. Sathya Sai Seetharaman as today's speaker. Satya is a computational scientist at STFC Rutherford Appleton Laboratory. He works on data infrastructure and workflows for the solid-state NMR crystallography community. He has a background that spans metamaterials, consumer electronics, and scientific computing. So he brings a very practical and cross-disciplinary view to FAIR data. Today, he will be introducing the materials database, which is being developed for UK NMR community, and how it supports researchers in making their data more findable, accessible, interoperable, and reusable. Dr. Sathya, over to you.
Thank you for the introduction, Mansoor. And thank you, PSDI, for giving me the opportunity to participate in another installment of the webinar series. And I would like to talk to you about our FAIR materials database today. And before I begin the talk, I would like to acknowledge and thank PSDI and CCPNC COSEC for the funding to the project. To give a brief overview of what we'll cover today in this talk. This talk is going to be both a bit of a retrospective on what we had achieved in terms of fair compliance with an existing proof of concept database, and look forward into what we are hoping to achieve adopting the Nomad database infrastructure and rebuilding our database. And over the past year, this project has been shaped not just by technical development, but also by strong community-driven collaboration and guidance across CCPNC, PSDI, FairMet, who are the consortium behind the Nomad database, and other PSDI partners. My aim today is to show what we have built, why we chose Nomad, and how this supports FAIR principles, and conclude the talk with brief mention of where we are headed next. And a bit about the community for which this database is being built. The CCPNC is one of the many collaborative computational projects that is funded through COSEC from the research councils. And CCPNC brings together experimental NMR researchers from multiple UK universities and pharmaceutical R&D teams from industry. And the core computational effort for developing the computational NMR software, several Python libraries, and NMR visualization tools are all provided by research software engineers of STFC, such as myself. A brief overview of what's already in the database and why it came about. Since there are at least 10 different density functional theory codes that can compute NMR parameters and output them in their own respective file formats, there was a need to standardize the DFT NMR data output so that the data becomes more interoperable and reusable within the community. And we want the data to all be easily findable and accessible as well. So addressing all the aspects of FAIR. And that is how the database, which I've mentioned, this is still the live version of our old database. The new version we are building is nearing completion and will be deployed soon, but the current active version is this one. So to unify the DFT computation outputs and make them fair, the Magres file format was created by CCPNC, and it is designed to be self-sufficient in that out of a computation, several information, all necessary information that you need to reproduce the data, such as the calculation metadata, including the DFT code, the versions, and the several parameters that were set to run the DFT computation, plus the crystal structure information that was used, plus the computed NMR parameter outputs. This is a simple file showing silicon structure and the two different NMR parameters, magnetic shielding and electric field gradient, computed per atomic site and stored as a flat 9x1 tensor, which is a flattened version of a 3x3 raw tensor, is self-sufficiently stored within the Magres. So the Magres file itself aims to be self-sufficient, and therefore our database stores only the Magres files, and any DFT files accompanying them obtained from the DFT computation are not stored in the database. So this gives the benefit of giving us a lightweight database. And to give a logistical distribution of entries in our database, we have about 5,800 entries with about a 60-40 split between organic and inorganic materials. And of all the organic materials that we have, 2,200 have linked ref codes to the Cambridge structural database from where the structures were originally obtained. To further talk about why this database was needed for the community, the initial needs of the Magres database was to avoid rerunning computations. Like if a particular research team or a researcher has already computed the NMR parameters for a particular polymorph, for example, and they have deposited results, it can be used as a quick elimination test for if I need to rerun the results, or if I can simply use these parameters and reuse them, or if I needed a small variation, then use the initial computational metadata that's stored with the Magres as a reference for me to adjust parameters if I want to rerun the computation under different conditions. And also to use the NMR parameters as guidance for designing experiments to retrieve typical NMR parameter ranges for specific materials and the elements in the material, and to estimate expected frequency ranges for that particular type of material before running an experiment. And also, the database was created with an aim of extracting molecular and substructure information from the crystal structures and storing these information so that in the future, as a more detailed structure and assessment into the material can be enabled. But this feature has not yet been available on the first version of the database, and this is a work for the future that I will talk about in the end. In terms of how far the database version 1 goes towards achieving the FAIR compliance, the strengths of the findable and accessible features of the database is that we make the NMR parameters searchable. I've included a demo of what our database looks like. We just need a simple ORCID authentication, and we make records searchable through a simple internal database reference, unit cell formula, any external database references such as CSD, ICSD, any publication licenses that the author has made available, and a free text chemical name search and publication DOI. In this example, I've included a partial name search for fumarate, for example, and I'm trying to filter the results down further. Say that, okay, I've obtained all fumarate results, but I'm specifically interested in materials that have the particular minimum and maximum values of magnetic shielding for carbon atoms alone. And I am interested in obtaining records that do not have a CC BY license. So I'm activating a exclusion condition on it, and that helps me filter the results. And as you can see, once you obtain the results, either all of the results can be downloaded in bulk, or particular results can be selected using checkboxes, and only those selections can be downloaded. And individual metadata for the individual entries can also be downloaded. So in terms of the challenges that we faced in making the data more findable and accessible, was that in terms of findability, we allowed users to enter chemical names, either IUPAC or common names by themselves when uploading structures. So as a result, you can search for these materials. But if you want to make the data more interoperable and findable outside your database, for example, via an external API, then there are no chemical identifiers such as inches and smiles in place that identify these materials and return results to a wider search externally. And also, since we use an internal database reference code, we do not have specific minted DOIs for uniquely identifying entries in our database. And this may be something of a downside when we publish datasets in journals, that they may or may not accept these MDB Magres database references as a viable one, as actually being able to assign DOIs is a more universal practice. And since the substructure search is not enabled, the amount of information that you can search for within the material is quite limited. And in terms of accessibility, though we don't have a public search API or command line access for this version of the database, the open access possibility of accessing all data without requiring to log in and having to log in only if you want to make data deposits in the database, enabling bulk downloads of data and making several licenses available for data distribution. They make up for the lack of an API tool, I think, for at least this size of a database. In terms of the interoperability and reusability of the database, as I mentioned, Magres was designed to be interoperable by itself. And we already have 3 DFT codes, Cast-up, Quantum, Espresso, and WASP, who have the provision to directly output their parameters in a Magres format if enabled. But there are a lot more DFT codes that can compute NMR parameters for which we have not yet added Magres support. So that kind of defeats the purpose and it makes it more challenging. So since the Optimate API layer was also not integrated into this version of the database, this is on our wish list to have in a database. But due to the lack of resources, we did not have time to integrate an Optimate layer into this version of the database. In terms of reusability, as I mentioned, to draw a highlight specifically to a calculation metadata block example from one of the uploads. A Cast-up since early versions has been a good example of sufficient metadata to output to reproduce a calculation, for example. But the early versions of Quantum Espresso, for example, have not really taken care to output sufficient metadata for calculation. And as a result, we are left with insufficient metadata for all the legacy Quantum Espresso data that has been uploaded to the database. And as I mentioned, since we store only Magres files in the database, it's quite challenging to retrace all the computations that were deposited and the original sources and try to obtain the calculation metadata information, since there are thousands of records. And this is something that we hoped to learn from in this proof of concept model of the database and to apply a more rigorous approach going forward. But by the way, in more recent versions of Quantum Espresso, we have had them add more detailed metadata. So this problem is out of the way. And the data provenance in general that people could include could be more detailed because Magres file can contain only so much information and a lot of operations that are happening ahead of the computations themselves get lost and those information are not captured. So in terms of why we wanted the Nomad database, the main motivation is, of course, they are handled by FAIRMAT and they have taken the FAIR compliance considerations into question for right since the beginning. And they have designed their infrastructure in such a way that a scientific community can be onboarded and they can readily adopt their infrastructure and create their own oasis, their own version of the Nomad database for their purposes that can be customized. And interoperability and reproducibility, as I mentioned, can be quite challenging to achieve in a standalone database within a niche scientific community. But Nomad offers a unified data model and more standardized parsers and the framework where we could link workflows from DFT codes directly to Magres, which we are working on. And all of these things promise to solve the main parts of the FAIR problems for us. And it also aligns us with the FAIRMAT and a wider material science community, making our data more visible and reusable. So that's one of the biggest benefits of working with Nomad. Since we also follow a community-informed metadata schema, Nomad has a preset style of schema design, which has given our opportunity to rebuild our NMR data schema from scratch, which I'll talk about next. And also a future potential to include more standard chemical identifiers because the schema is robust, but also quite flexible, allowing for more inclusions as the database expands and more functionalities are added to the database. And also we wanted to customize the schema to include more legacy metadata that we stored specific to the CCPNC community. And also, since Nomad has out-of-the-box Optimade API that can be programmed to work with a custom community's data and extendable to CCPNC needs, this was also a major wow factor for us. And Nomad has an inbuilt data provenance tracking and workflow linking that can be programmable into the parsers that we design. We started from the very basic building blocks for our database. The very first body of work we undertook was to revisit the schema that we need to serve the database to the users, because we identified the schema requirements to be made of several subdivisions, and it is always the best to address metadata and schema first before building anything for a database. For example, the very basic, broader building block would be to redefine and expand the core NMR parameters, because that's the main constituents of the Magris files, and that's what users want to search for in the database as a very minimum requirement. So we started from there, and we took this opportunity to define a solid NMR parameter schema, how each new quantity is defined, how they are made available from the input files, and how we are going to store them, etc. This data block would benefit both the CCPNC community when we incorporate this package into our Oasis database, but we also make this schema package available to the Nomad community itself on the central Nomad database, so that the wider NMR users, if they prefer to use the central Nomad database, they still have access to this core NMR schema. And on top of it, the legacy data that we want to migrate from our old database to the new database that we are building, that incorporates community-specific metadata that we have captured, and we want to retain also for future uploads to capture the same information to be consistent with what we store. This base schema required a further customization, which we developed as a separate plugin package, but this could just be added on top of the earlier plugin by creating dependencies. And this was such a nice flexible plugin structure to work with on Nomad. Similarly, when we also want to add more parsing capability in the future, as I mentioned, we want to add advanced searching capabilities for crystal structures in our database. So that adds another layer of specialized schema definition to assist the community's usage. On the right, I have mentioned separately another data block where we could define more standard chemical identifiers, cheminformatics identifiers such as inches and smiles strings as data quantities. This benefits not just the CCPNC Oasis, but I think Optimade are also working on creating a namespace for cheminformatics, and PSDI are working with Optimade Consortia as well to create a PSDI namespace. So since PSDI have their data cross-search, having these quantities as part of a schema helps us expose our data to PSDI's cross-search and other external databases more easily. So we have taken this very flexible database design approach. And chipping away at the different building blocks of the schema itself, I wanted to mention quickly core NMR parameters, what we did. In the old version of the database, we supported searching for only magnetic shielding and electric field gradient, as you may have seen from the search menu in the demo of the old database that I had added. But having the opportunity to redefine the schema has helped us bring the CCPNC community and their inputs together into contributing more, because Magris has provision to support more computed NMR parameters such as indirect spin-spin coupling, which gives parameters not only just for individual atomic sites within a structure, but also it characterizes interaction between several atomic sites between each other, and the magnetic susceptibility tensor. Besides these raw tensor parameters that could be computed directly from the DFT codes that are available via Magris files, the main parameters that are actually of interest for users to search in data ranges. For example, when people are searching for magnetic shielding, they are not searching for magnetic shielding tensor values, but a more derived quantity such as an isotropic value in the magnetic shielding, and say that I want data for this particular element within a certain data range. So the schema also helped us define all these derivable quantities from these tenses that we could easily store in the database. When the data is deposited, the parser handles all seamlessly and stores it in the database. And going to work with Nomad also opened up more collaborations for us with a company called Exact Lab and researchers from the Central National Research Institute in Italy and the University of Trieste. Mainly, they were also working with Nomad to make improvements to NMR parameters, but specifically for quantum espresso computations. And they worked together with us and they contributed some parameters to our schema for the electron paramagnetic resonance as well, hyperfine tenses and electron G factor variations, which could be beneficial to both NMR and as an extension to the muon research community. And this was such a great opportunity. And an important thing to mention is that this collaboration led us to seek some guidance from Quantum Espresso's developers as well. And working with Magris files and Quantum Espresso together, again, that helped them identify a few parametric problems that they had in their code that they were able to fix as well. So this is all multiple problems solved at once, a trident approach, I would say. I've added a link to the schema package and the Magris parser that we have developed, which are both housed within Fairmat's GitHub pages because they are available both for our Oasis and the central Magris. Central Nomad database, as I mentioned. And very quickly, before I show you the demo of how far we have achieved with the current version of the database, I want to tell you what we have done to customize the schema and parser. The first problem is to migrate all the legacy data from our old database to the new database, which contains specialized metadata. And all the metadata that we are carrying over from the old database could be just packed into a JSON file. And uploading both a Magris and an accompanying JSON file with the same name together, we programmed our parser to recognize these accompanying JSON files as auxiliary files that are meant to carry metadata information and automatically extract and store these information into the records automatically. And we wanted to, for consistency, maintain these custom data capture for new uploads that happen in the future, especially for bulk Magris uploads as well, as in the case when people publish data sets that are part of published paper or just a published data set from a PhD research, for example, and a machine learned data set, etc. And when people upload these data sets to the database, we make available a CSV file where users can mention all the files in their upload by name and add all the necessary metadata in the CSV file. And our parser will recognize this CSV file as well as meant for bulk uploads. And similarly, it can extract the same parameters it looks for in a JSON file and associate it with the specific entries. And for all new uploads that may be just single Magris uploads, we went with a simpler electronic lab notebook approach where our parser recognizes that there is no accompanying metadata file. So it creates an electronic lab notebook in itself and lets the user enter the metadata by themselves. So in this demo, I would like to show what we have achieved in our database. This is not yet deployed, by the way, as I mentioned, but we aim to have it deployed in the next couple of months with PSDI help. And I wanted to begin by talking about the data findability aspect, like how we have managed to provide the same findability features in this database as we did in the old. Our first priority is to retain functionality and then build on top of it. Here, we have designed a custom CCPNC NMR app, which lets you view all the entries at once. And of course, the first thing that you see when you come in is on the dashboard is a periodic table that lets you filter results just by selecting, I want materials with so-and-so elements. By clicking and filtering, you can. But I think for today's example, I have taken up maybe a simple use case where a user has maybe read a paper and about titanium doped yttrium stannate, and they want to come to our database to find it. One of the easiest way to find it is to go to the material properties menu, selected from the chemical name on the list. But this is quite straightforward for this example because this particular material has relatively a higher number of entries and it was high up on the list, easy to locate. But users can also just type the material name in the name search and identical results as before. It's just that in the chemical name search in Elasticsearch interface for now, we are offering exact string searches. For partial material searches, we are working on customizations to make this available soon, and this will be available upon deployment. And similar to those searches, like I mentioned, I can also try to filter this material just by clicking the constituent material elements that are part of this. So if I click titanium, yttrium, and stannum, this interestingly will give me two sets of material groups, of which I can filter it further by selecting titanium, doped yttrium, stannate. That's what I'm interested in. Give me all the results for this material. So that's already three different ways of searching for the material as long as you know what you're looking for. But since I mentioned that in this example, a user read a particular paper and wanted to find the data set in the database, they could also just search for the data set directly by the DOI of the material. And besides these specific targeted searches, if a user wants to take a more broader road, for example, they can look for chemical formulas of the material, search by example, and narrow down the results by specifying I want all the results that have 3 or 4 constituent total elements in the material, not more, not less. And also, if the users are interested in looking for calculations done by a specific DFT code, a specific DFT code version, they can filter those in the menu. And similarly, specific functionals that were used in the DFT computation, as long as the correct metadata was provided at the time of uploading. If not, something like not processed will appear, which is a problem. And we aim to eliminate these problems in future uploads by making the metadata capture more rigorous at the time of uploads. Of course, you can also see the users can also filter records by an author's name, internal Magres DB record, the database reference code, and DOIs and licenses. Though Nomad by default makes all their records publishable by CC BY license, since in our old database we retained multiple licensing options, we are carrying that over. And in our data filters, we are making our records searchable by those same licenses that our users made available at the time of upload. Coming back to the example that I was talking about, the titanium doped yttrium stannate, if you migrate into one of the individual entries that comes up from the results immediately, you can see all the associated metadata such as the DFT code information, DOI, and the author's ORCID profile. And Nomad's crystal structure view has already extracted the information that we input from the Magres atoms data block, and it's managed to create a crystal structure preview. And if you're interested in looking directly at the NMR parameters that were calculated, you can migrate to the data section, look into the outputs and at the individual NMR parameters. And all these O's are actually different oxygen atoms within the material. And we are going to make these labels rather than just atomic symbols. We will be making them more descriptive soon with custom labels included to identify specific atomic sites within the material. But once you are in, you can view the raw tensor and also the individual calculated derived quantities, as I mentioned. And these are the quantities that we are aiming to make searchable via the search menus, similar to all the other metadata parameters that you saw earlier. One of the challenges we are working through resolving it with these targeted NMR parameters site-specific search is that in Elasticsearch, to make these nested queries available for custom schemas such as the CCPNC, more customization needs to be done. And we are working with Nomad to make that achievable in a near future, very short time window frame. I think, yeah, that's all I had to say about on this slide. But all the other metadata parameters such as the chemical formula, the DFT code information, the cell information that were all necessary to make the other parts of the app work better are all included here. And the custom schema that we mentioned that carries all the legacy data information from the CCPNC metadata are all stored inside this data block that are all extracted from the metadata files, either JSON or CSV, or even better, the electronic lab notebook I showed. earlier. So in this example, I also want to show you next how our Magres parser works. I wanted to show you the parsing in action. So I wanted to show you two examples today, one bulk upload and one isolated Magres upload that creates an electronic lab notebook. And for this purpose of depositing the data, you need to be logged in. As you can see, I am. I'm going to create a test upload specifically for this PSDI webinar, and I'm going to name it bulk upload example and save it. And I have pre-obtained some of these legacy Magres data from our database as an example. And as a practice in our old database, as I mentioned, this is the CSV file template that uses fill up to mention the individual file names under file name and fill up the all other associated metadata such as the chemical name, licensing information, DOI, external database information, any other useful notes that they want to make available for people searching their data. To save time, I've already packed this data set inside a zip file, and the file deposition is as simple as drag and drop inside the upload, and you can immediately see the cogs turning and the status displaying, and all files are passing. And once the success status appear, you just wait for the cleanup to complete, and you can explore the entries immediately. And if you look at the files, even though you are looking at the entry for a particular file, all the entries that were jointly uploaded in that group and the metadata file that was uploaded can all be viewed in one place and can also be downloaded as a bulk again. And looking at the data, as I mentioned, I'm just showing you an example of the CSV parsing in action. The information that was entered in the CSV file has been extracted, and it is associated with each individual Magres file in that bulk upload. The next example that I want to show is an individual Magres file upload. And why we decided to do things differently for an isolated Magres file approach is that making a user fill CSV file just for one Magres file, like one Magres and one CSV file, seems to be a bit of a clunky approach. So we thought, let's make the parser do the work of generating a metadata file. And once the parser identifies that there are no other accompanying metadata files, it automatically creates an electronic lab notebook entry that the user can view. And all the information that we made available on our upload forms on the old database has been made available here. And to save time, I have pre-filled the information for this form. And one of the things that you can enter here is also the author's ORCID ID, because by default, the person who's uploading the data is made the author also, although an admin can change this and reassign ownership. It's also useful at the time of data deposition to capture the ORCID information. Besides that, the users can enter chemical name. We are making available the same licensing options, the same set of external database reference options, and field to provide a custom notes. And once you click save in the electronic lab notebook, the normalizer of the parser automatically works in the background, identifies that a change in this overall upload has happened, and it extracts this information and reruns the metadata parsing part, and it extracts that information and drops it inside the CCPNC metadata section of this record. So yeah, we have addressed the findability and accessibility actions to a greater extent in the updates so far, although, as I mentioned, some minor improvements and tweaks need to be made to make it complete. And the current work in progress for us is the interoperability and reusability features. We are currently in talks again with Nomad to see how far their existing Nomad API can support custom quantity, because they can already support base quantities that are already defined within the Optimate's namespace. But there is also room for defining a custom namespace for our community and making Optimate Consortium aware of the existence of this namespace and asking them for support to include Optimate support for these quantities, following the specific convention recommended by Optimate. The Nomad team have also, as a short, quick fire solution, recommended us to use a tool like Optimate Maker, add it as a dependency, and it can pull all the raw data files and identify the crystal structures and generate data sets, expose the data in an Optimate compliant format. I've just started working with Optimate Maker, so to my understanding, it's working. That's how it works. We are addressing the reusability factor, as I mentioned, along with a Magres file. Although I have not shown in this example, we are working on possibility of, along with the Magres file outputs, for users to also be able to include DFT code outputs and any other operations that were performed prior to the DFT computation, such as geometry optimization to relax the crystal structures. And we are currently focusing on adding the support for cast-up quantum espresso and by extension to WASP a bit later. Because we don't have any WASP computed files in the Magres database, we are focusing on cast-up and QE first. Since these geometry optimization and the other DFT codes themselves have individual parsers within Nomad that extracts quantities, we just need to make sure that the Magres parser is also smart enough to detect the presence of these files, so that once the other parsers extract the necessary parameters and keep it in their data bins, the Magres workflow can contact the other parser workflows and create an interlinked workflow and present it as single unified provenance map for easier data tracking. Since I began the presentation with the need of the earlier version of the CCPNC database and the early use cases, I would like to draw a conclusion to the presentation by mentioning how the use cases are getting more complicated and evolved for the community, and why we need to work on a more advanced searchability of our data. And the recent survey this year from our community expressed a desire within the community to be able to look deeper within the crystal structures that are in the material, look at specific atoms within a specific functional groups in a material, or a functional group in a material being in the vicinity of another special type of atomic groups of atoms or molecules, and seeing how the NMR parameters in those vicinity get affected. And similarly, studying how parameters change in specific linkages between atoms and also in the vicinity of other specific types of atoms. And to talk about what we are working once we deploy as our first installation of the database, and assuming the functionalities that we were already able to provide on the old database, what we want to make available in the future work that builds on this earlier version is to further advance the searchability of materials by offering substructure searching. And for this, we conducted a workshop with the CCDC Optimate experts, PSDI and CCPNC participants as well, to discuss the use cases that I showed earlier, the evolving use cases, definitively create a roadmap of what's needed and how can we go about achieving this, all while remaining open source and not become a subscription-based service, and make this user-friendly advanced search possible. And for this, we have already been testing a workflow using one of CCPNC's crystal structure processing tool, Soprano, and in combination with OpenBabel to extract bonding information and then convert it into a smarter cheminformatics information. And also, I wanted to mention, though we have not extensively started working on this tool, thanks to Dr. Shin Yong from CCP5, who's developing this data tool, which builds on similar tools, DL Poly and DL Field, that he has already developed for biological molecular structures in the past. And by extension, we are testing this data tool for the CCPNC use case to extract more detailed information on interatomic linkages, plus extracting specific functional groups and converting all this into cheminformatics information and storing this, and looking at making this available via Optimate and other cross-search like PSDI's cross-search tool, etc. And this is one major body of future work. And besides the workflow linking with the DFT to Magres that I mentioned, since Nomad has a wealth of other DFT parsers support inherently built, we wanted to also make maybe an interoperability package that's external to Nomad itself that converts DFT code outputs. We identify the predominantly preferred DFT code outputs by the community and write wrapper packages that convert this DFT code outputs, extract NMR parameters, output in a macros format, so that when these files are combined with actual DFT code outputs that don't output macros outputs themselves, and then deposit in the database, then build that workflow, as I mentioned 2 slides before, and updating the macros parser to detect these and create workflows. That's all coming in the next year, hopefully. Thank you, everyone, and thank you, PSDI, once again for this opportunity to talk about the work that I've been doing. And I'll aim to answer all your questions here today, but you can feel free to reach out to me by email or on my Discord to discuss further topics of interest. Thank you.
Thank you, Dr. Sathya. That was an excellent presentation. I really appreciate the demos. It was really helpful. We'll now open the floor to questions. From your experience working with the NMR community and developing the OASIS database, if you had to give one key takeaway message for the researchers who are starting their own FAIR data sets, what it would be?
Yeah, I think the key is to start small and define all the things that are important first, identify the basic building blocks. Don't leave metadata for later. I think metadata and identifying what's important, what needs to be consistently stored and be made available to the entire community, identifying that I think would be a very important first step. When we started, one of the very first things we did was work with the metadata working group and Eileen from PSDI to identify our community's metadata needs.
Yeah.
And I think the key is to also not underestimate the FAIR, because it can quickly get out of hand. It has several different aspects to it. You need to identify what's important just for your community and prioritize what you need to do. Start small, but build on. I think that would be my learning.
How else PSDI helped or supported this project?
I think PSDI have been the ones to first recommend the Nomad infrastructure for us for the specific requirements that we put forth, because we were considering different possibilities within the time frame that we had in mind for the project. Rebuilding from scratch was not an option, but we were also thinking about partially pre-built templates and just customizing them from scratch. But Fairmat and Nomad was a complete package on its own, and we just needed to adapt and customize it. And as I mentioned already, the metadata working group helped us a great deal to standardize our schema, plus the technical working group, the infrastructure working group, like all the different teams within PSDI. We have always been in touch from time to time to talk about our deadlines and all the things we need. They've always supported us.
You mentioned in your talk about when you moved the legacy data. So what were the challenges when you faced during the legacy data migration? Did you face any challenges?
The challenge was that it's not as simple as just packing all the files from the database, take it into a one zip archive, 5,000 files, just drop it and expect things to be. I think very specialized scripting needed to be done to identify, because when you want to publish these data sets on the new database, because Nomad makes available so many different facets in which you can expose metadata, such as DOI and the different DFT codes information, you need to make sure that your uploading script makes sure that it categorizes your data based on published and unpublished data sets. It takes into account the original authors of the data sets, because you upload as an administrator and then you change ownership of the data. So I think that took some time to tinker around and get right for me, and playing around with the menus, identifying what's not working, and working with the community. But thankfully, Nomad also has got a very supportive developer community on Discord, where you can get almost instantaneous help on your questions and topics.
Thank you again. Just a couple of housekeeping things before we wind up. So the PSDI resources are live now. This is our new website. Please take a look, where you will find a wide range of resources to help to support your work. This includes data services, tools, guidance, materials, and case studies, all designed to help you navigate different aspects of research data management and open research practices. Feel free to contact us if you have any questions. We have a couple of events, upcoming events. You can see the details on our events page. In January, we have another webinar by Dr. Elliot and Dr. Aline about trusted and reproducible workflows for machine learned interatomic potentials. There is also a machine learning school, April 13th to 17th. All these details you can find on our events page, and all the registration links are there. All our webinars will be posted on our YouTube channel, so feel free to go and take a look. That concludes today's webinar. Thank you all. Big thank you for Dr. Sathya for an excellent presentation. Wishing you all a good rest of day, and we hope to see you on another PSDI event. And thank you.